Okay, so let me continue this chapter, sampling distribution of mean. Okay, so let's see, we have a random sample of size n. From x, which is n mu sigma squared. Now, if we want to find the distribution of this 1 over n sigma x. Okay. Well, we know that this, by the theorem, sigma xi is itself has normal distribution. Is also normal with n mu and n sigma squared. That was one of the theorems I explained last time, and now I want 1 over n. So let's find E of 1 over n of this thing. So that is 1 over n, E of this. Which is 1 over n times n mu, which is mu. And the variance of this thing that's 1 over n squared, remember, that's 1 over n squared variance of. So 1 over n squared n sigma squared, which is sigma squared over n. So x bar n, in fact, is n mu sigma squared over n. Okay. Now let's see what the central limit theorem tells me as n goes to infinity. So let me erase this thing. I have x bar n, that is n mu sigma squared over n. So let's define Zn like in central limit theorem. We have x bar n minus mu of this divided by square root of n, which is the standard deviation, sigma over square root. Okay. Now by central limit theorem, this Cn approaches to some z in distribution that is n0. So as n gets larger and larger, that is getting closer and closer to standard normal distribution. So we can treat that as n01 for n large. Okay, so the other one is sampling distribution difference of two means. Okay, so sampling distribution of difference of two means. Well, I have given enough explanation in the notes, but let me just write it here. So I have two distributions. So I have, for one of them, I have this one, and let's just write I here, and this is mu, say I, and sigma squared I over and I is 1 and 2. So I have two distributions, and the two distributions are one that's n mu 1 sigma 1, the other one n mu 2 sigma 2, and we found it here that this guy here is normal with mu I and sigma I squared over n I. Now we need a distribution for x bar n I minus x, 2 minus 1, say. 2 minus 1. Well, this is the difference between two normal distributions. So that's, again, normal. So let's find its mean. We can, well, let's find its mean. It's very easy. Just find the mean. The mean of S is the mean of the first one, mu 2 minus mu 1. In fact, that's e of x and 2 minus e of x and 1, which is mu 2 minus mu 1. The variance is this, so I have x bar and 2 minus x bar and 1. And I assume that these are all independent, so these two are independent. And being independent, variance kind of distributes over this negative, but in this way. Remember, for variance, we had that. And that's, in fact, there's a 1 here and a minus 1 here. So there's a 1 here and minus 1 here. So it's, in fact, 1 squared variance of the first one plus minus 1 squared variance of the second one. First one, second one. So this will be sigma squared 2 over n2 plus sigma squared 1 over n1. So the variances are not subtracted. There's no, they are not subtracted. So they're added because of this property of variance. When you have independence, you can do that, but anyway, you need to be careful about the coefficients. They are squared. Okay, so let's write it here, and so x bar n2 minus x bar n1, we found that this is in fact normal with mu 2 minus mu 1 comma sigma 2 squared n2 plus sigma 1 squared n1. Okay, so in order to use the central limit theorem, we need this, well, what should I say, n1 and 2, something like that. So the random variable minus the mean of that divided by its standard deviation, which is square root of this thing. Sigma 2 squared over n2 plus sigma 1 squared over n1. So this approaches as n1 n2 get large enough to say a z, which is n0, 1. So as n1 n2 get large enough, we can say that this thing here, the z, is a good approximation. I mean, it's almost standard normal. So we can treat that as a standard normal in what we will be doing, and we will see that. So That was the difference. And next is sampling distribution of S2. So that is well, what was S squared? S squared was 1 over n minus 1 sigma. Let's just write xk minus x1 and we will see why we need n minus 1 over there in the next chapter, in fact. Okay, so that is sample variance squared the sample variance, so we need the sample distribution of this thing. Okay, now we need to find, well, this has to do with something we call t-distribution. So let's just find out the distribution of, well, let us see why we need that. So just look at this thing. When we expand this thing, we have xk squared and also x bar n squared. And we know that this is normal and this is also normal because we are dealing with normal distribution. So we are dealing with normal distribution squared. So what is distribution of normal distribution squared? That is what we want. So that is, in fact, as you see, that's x squared, and we will see that's what we call a chi squared. So let me find it. So let y be x squared, and x is standard normal. Okay. So in order to find distribution of y, which I mean, the distribution has there are two things we usually find. One is the PDF and the other one is the CDF. When we want to find distribution of something like this is in fact a function of x, so that's x squared. When we want to do this, we find CDF first, and everything here is continuous. I'm not discrete or continuous discrete, something like that. So but this is continuous. So we have to find the CDF. To find the CDF, and since the CDF is continuous, the derivative of that CDF, in fact, is the PDF. So let's find the PDF from the CDF. This is a good practice. So what is a CDF? CDF is a function of, say, we are using y, so a function of y. That is P of this capital Y is less than y, which is probability that x squared is less than y. And remember, when I write this thing and y is x squared, then y is positive. So I'm assuming that y is non-negative. So this is equal to, since y is non-negative, I can write it like this. X is less than equal to square root of y, bigger than minus square root of y. Okay? But x is standard normal, so this probability is in fact from minus square root of y to square root of y, 1 over 2 pi, that is the PDF of x when it is standard normal minus x squared over 2. That's x dx. Okay, so that is that probability. So I have the CDF. This is the. How can I find the PDF? PDF, in fact, is the derivative of this, dfy by dy. The PDF is the derivative of this So let's find the derivative. And I just write the result for you. So d by dy of this integral remember from Calc 1, let's Calc 2, I guess. Calc 2, that this is in fact the fundamental theorem of calc, that is derivative of this integral equals what? So, well, that fundamental theorem usually has like a to x, for example. But if you have this thing, this is like you have to use the chain rule to find this, and so that's the derivative of this one minus the derivative of this one times e evaluated at these two. So let me write it. So I have 1 over 2 pi. Oh, sure. And let's call it up to pi. And well, let me just write the result. So that result will be this. I can see here what I have here, y minus 1. Okay. So this is the end result. So the PDF of this distribution, which we call it y, is this. Now, what is it? It looks like what? If we go back a few chapters, this is in fact what we call gamma distribution, right? So this y has gamma distribution with, in this case, it is 1/2 and 2. Now the gamma distribution alpha beta, it has there are two different ways to define it. This is the way that it's defined in this book. So when you say alpha and beta, I don't get confused. So this with this definition, in fact, is this. Now, well, that was just for 1x. And we are dealing with a random sample which has more than 1x. We have n x's here, and each one of them is like normal. So what happens when we find s squared and we have lots of them added together? So that is in fact another theorem which let me just find the. So we have this theorem on gamma distributions. So if each y, which is x squared, is as gamma distribution, then the sum is the sum of some gamma distributions. So we want to see what sum of gamma distributions is. So sum of, well, I'm not going to prove it, but I guess I have given some proof. No. But anyway, so the sum of gamma distributions so if I have y1 is gamma alpha 1 beta, y1 is gamma alpha 1 beta, and y2 is gamma alpha 2 beta, then y1 plus y2 is gamma alpha 1 plus alpha 2. So the beta should be fixed here. So if beta is fixed and alpha is changing, then we get this. So sum of some xi, sum of xi squares where each xi is normal, mu, and sigma, mu say I and sigma I squared, something like that, then it is in fact, so let me, oh, well, that's okay. So then each one of them, oh, this should be 0. So this should be 0, 1, because that was through. If I have some sum of these things, xi squared, that has a gamma. In fact, if I goes from 1 to n, I have n of these things, n over 2 and 2, and that is in fact what we call chi-squared, with n degrees of freedom. Okay? So, let's continue. I don't know if I should write all these things here, but it's okay. Let me. But using this fact, we can now go back to s squared. So s squared was 1 over n minus 1 sigma k from 1 to n xk minus x bar n squared. This well, let me find that identity that we used. Yep. Well, I'm not going to write this down. It takes some time, and I have the proof in the notes for you. But this is what happens in the end. In the end, we have n minus 1 times s squared over sigma squared, and that is chi squared n minus 1. So, okay, so this quotient here has distribution chi squared n minus 1. Now, as I said, I'll say it again, you can refer to the notes and you would see a proof which is based on some identity for, in fact, this. This thing splits in 2, and then using that split, we can prove this fact. Okay, so that is distribution for s squared. So in fact, you are not finding distribution of s squared, you are finding distribution of something else, something which has s squared in it. Using this, you will see in the next chapter the confidence intervals, that how we can find confidence intervals for certain things. So, and well, let's see. Then there is another. The T distribution. So we have another distribution to discuss, and that is the T distribution. So T distribution is this. If I have x n0, 1, and I have y, which is chi squared. Y is chi squared, and they're independent. Then the quotient of them, x over y divided by m, in fact, is what we call T distribution. And that is T distribution with m degrees of freedom. Okay, now let's look at this thing. Well, how did we find chi squared? Chi squared, we find chi squared by squaring this guy here. normal distribution. So normal distribution squared is chi-squared. And this is 1/2, not 2. Now what's going on? We have a normal distribution here, and this is like a chi-squared divided by some constant to power 1/2. So it's like square root of this thing. Well, square root of this thing doesn't go back to normal distribution. It's something else. So it's amazing that this, which looks like a normal divided by a normal, which the denominator is not normal, but that's like square root of chi-squared, is an amazingly useful distribution. Now, why is it so? Where do we use this thing? You will see that when some population is given to us and we want to find some information about its mean, we don't have anything. We don't even have its standard deviation, sigma square variance. So we find a square, in fact. And that formula, this thing here that we had x bar, remember, x bar minus mu, denominator was sigma, but if we don't have sigma, we have to deal with this. And you see that this, we know it's in the end, it's normal distribution. This is normal distribution at any end. And this one, we know that it is chi-squared. So we have normal divided by chi-squared. Normal divided by chi-squared, and that was in fact s squared is chi-squared. So s over square root of n is like this 1 to power 1/2. So this has some kind of t distribution. We will see that in the next chapter. That's why studying t distribution is crucial, because most often we don't have a sigma squared. We don't have the variance of the population. We just find the variance of the sample, that sample variance, s squared. So that's where it's used. Okay, now finding its PDF, in fact, needs some more knowledge, a lot more, and that has to do with transformations, and I'm not going to find it, and there's a formula for that which you can see in the book and also in the notes. Well, that's all, in fact, what I wrote over here. So that's the theorem. And the T, this has T distribution. It is T and minus 1. Okay. Well, I leave this to you. It's very easy to see why this is t n minus 1. Let me see if there is anything else left here. I don't see it. But I have given you enough examples, and I have clarified so many things in the notes. So you can refer to the notes. And also I have given some codes in R. And yeah, so that's about distributions. So let me stop here.